genomewide association studies. So this thesis has been accepted by the faculty to be defended today, and we have some supervisors. We have Didi Montes, we have Esben Aarhus, and Anders Børlum, who has supervised Veera during his studies during Aarhus. And for the opponents, we have Catherine Lewis from England and Veera Davis from the States, and they will, after the presentation from Veera, they will ask him difficult questions and try to put him on the spot, finding any problem that might come to their mind. Yes. And yeah. So I can remember from the old days, we should tell you to turn off your phones. So I suppose after the presentation we'll have a short break before the opponents will ask the questions. And after the questions have been asked, we will ask you to leave the room for a short time, and then the opponent will make a decision on the defense, and we will come back. So, thank you, and we'll give the word to Veera.
Thank you. Good afternoon, everyone. So, the title of my PhD dissertation is Disentangling the Genetics of Cognition through Genomewide Association Studies. So, I'll first start with my acknowledgements. So, I express my sincere thanks to my supervisors for supporting me and giving me the opportunity in the first place to do this research. And I also thank the wonderful assessment committee for giving a timely review and very valuable feedback and comments. Then the Graduate School of Health for supporting me through a fully funded PhD scholarship, and the Lundbeck Foundation, whose generous funding to eyesight has made a lot of projects possible, and one of those projects is my PhD dissertation. And last but not the least, all my collaborators and their funding bodies without whom this dissertation would not be possible. So this PhD dissertation has 4 manuscripts in it, and I'm going to talk about 3 manuscripts for the presentation, and the 4th one will be reserved for the discussion section because of the time constraint. This is the structure of the presentation. So we'll start with the general introduction and related concepts, then individual studies, and final closing remarks. So general introduction. So this PhD dissertation is about cognition. So what is cognition? Cognition is simply, the process of thinking. So what you do when you think, you process information, and how you get this information from your surrounding environments through your various sensory perceptions, and you process this information and then you act on it. So when the outcome of your reaction is not what you intended for, you store your experience in your memory. When you come across a similar situation in the future, you retrieve this memory and then you change your reaction. All this is possible because of our various cognitive abilities such as attention, memory, motor skills, language, etc. So these cognitive abilities, we acquire these cognitive abilities from birth at a different time point in our life as we grow, and this simply reflects our brain development. And these cognitive abilities vary from person to person, and this variation can be due to environmental factors and genetic factors. And this PhD dissertation, we are going to deal with the genetic factors of these cognitive abilities. Our cognitive abilities are highly influenced by our genes. So children born to parents who are good in math naturally tend to be good in math, and children who are born to parents who are good in music naturally tend to be good in music. It just simply reflects the high influence of the genes on these cognitive abilities. So why it's important to study the genetics of cognitive abilities? Individuals with disorders such as psychiatric disorders, schizophrenia, major depression, a lot of childhood developmental disorders like speech disorders, dyslexia, these people suffer from mild to moderate cognitive dysfunction. We do not know why. So in order to understand this, we need an understanding of the genetic mechanisms of cognitive ability. So before I start the individual studies, I'm going to give you some related concepts, going to explain about some related concepts. So this whole PhD dissertation is based on a method called genomewide association study. So I'm going to tell you about what is genomewide association study and two important analysis that you can do from genomewide association study, which is very important for you to understand the individual studies. So what is genomewide association study? In order to understand what is a genomewide association study, you need to first understand what is a genetic association study. Let us consider just a single variant in our genome where A is replaced by T, and you want to know if this variant puts you at risk for a disease, say schizophrenia. And how will you know that? How will you test it? So all you have to do is collect individuals with schizophrenia, who are called cases, and individuals without schizophrenia, who are called controls. You genotype them for the SNP for this variant and then see how frequent the SNP occurs among cases and controls. If the SNP occurs more frequently in cases, then you say it is as a risk variant, meaning if you have the variant, you have some risk of acquiring the disease. If the variant is present in more frequency in controls than cases, then you call it as a protective variant, meaning if you have the variant, then you might have some kind of protection against the disease. So that is how you study, you do a genetic association study. So at the end of the analysis, what you get is two important values. One is p-value and the other one is beta value. P-value tells you if the association is statistically significant, and beta value tells you if that's the strength of the association as well as the direction of the association. If it's positive, then it's a risk variant. If it's negative, then it's a protective variant. So in genome-wide association study, we do this, but not just for one variant, but we do this for like millions of variants. On average, we study like 8 million to 10 million variants in a genome-wide association study. So we are doing like 8 million tests. So by chance, we will see like thousands and thousands of variants that has a p-value less than 0.05. So the p-value threshold of 0.05 is no longer a valid threshold in this scenario. So we use a more stringent threshold, that is p-value less than 5 into 10 to the power minus 8. So I said that we are studying 8 million variants. What is special about this 8 million variants? We have like more than 80 million variants in our genome. So these 8 million variants are called as common variants, meaning they occur more commonly in the population, more than 1% of the population. Why is it important to study this specific set of variants, common variants? So in this plot, what you see is that in the x-axis you see the allele frequency, in the y-axis you see the effect size. So you can see that as the allele frequency increases, the effect size decreases. So this is a typical spectrum where you take any genetic studies, it will fall within the spectrum. And what is at the ends of the spectrum? So at one end, you have what are called as like extremely rare variants. So these variants will cause the disease, and these diseases are said to have 100% penetrance. It means if you have the variant, you have the disease. So that are called typical monogenic diseases like cystic fibrosis, sickle cell anemia, hemophilia, etc. And in the other end, you have common variants. So these common variants have very variable amount of penetrance. That means if you have the variants, not always you will get the disease, but each variant will increase the odds of you getting the disease a little bit. So the more number of common variants you have, the odds of getting the disease is more. And this is typically what happens in traits like type 2 diabetes, hypertension, schizophrenia, and also like height and BMI. So they are called as polygenic disease. So they fall on the other end of the spectrum, and that is what we actually study in the genome-wide association study. So we have this GWAS summary statistics from all the 8 million variants. Like there are a lot of information you can study from this GWAS summary statistics, and I'm going to tell you about two important analyses that is essential for this PhD dissertation. One is genetic correlation analysis. So consider two phenotypes, let's say schizophrenia and then intelligence. So now I did a GWAS of schizophrenia and then the GWAS of intelligence. Then I have like all the summary statistics you can see here. So what I'm going to do is I'm going to take only the beta values of these SNPs from the two traits, and then I'm going to correlate them together to see what is the correlation. And I see there is a negative correlation. So what will I infer from this finding? So it means that the variance that increases your risk for schizophrenia decreases your IQ. I can also put it in this way. The variance that increases your IQ protects you against acquiring schizophrenia. So this correlation is not some simple Pearson correlation or a Spearman correlation that we do regularly in statistics, but this is done using a special method called linkage disequilibrium regression or L-score regression. So what's special about this is it's considered the local correlation between the SNPs that's very important in the scenario of the genome-wide association study. So another important message here is that from this you cannot infer any causality, that is you cannot tell that schizophrenia will lead to low IQ or the high IQ will lead to a protection against schizophrenia. It's just the correlation and we cannot infer any causal direction of effect from this finding. Polygenic risk score. So what is polygenic risk score? So polygenic risk score, to simply put, is a cumulative risk of an individual for a disease. And you calculate this risk based on multiple genetic variations, typically millions of variants. To understand this, let's take a very simple scenario where we have 3 SNPs. So here we have the summary statistics for 3 SNPs for a phenotype, let's say schizophrenia. Then how will you, so let's say I have to calculate the polygenic risk score of this individual based on these 3 SNPs. How will I do that? So I just have to collect the blood from this patient and then genotype for him for the 3 SNPs, and then I identify the genotypes. Then I count the number of risk alleles at each position. He has 1 risk allele in this position, 2 here and 0 here. So I just multiply this number of risk alleles with the betas, and then I get these numbers, then I sum them together, and I will get a single number for each individual, and this single number is the polygenic risk score of this individual for schizophrenia. Like this, if you do this estimation for, like, say, thousands of individuals in a population, and you plot the distribution of these risk scores, what you will see is a typical bell-shaped distribution. So what does this mean? Like, most of the individuals in the population will lie somewhere in the center of this spectrum. So they will have equal number of risk variants, equal number of protective variants, which will cancel each other. So their risk is very neutral and they lie in the center. But there are some people who will have more risk variants than protective variants, and they will be lying somewhere in this side of the spectrum, and some will have more protective variants and they will lie under this end of the spectrum. And that's how you calculate the polygenic risk score and interpret the result from the polygenic risk score. So then finally, I tell a little bit about this Danish case cohort eyesight, which is actually the foundation of this entire PhD dissertation. So what is eyesight? Eyesight is a Danish case cohort and it's established by Lundbeck Foundation. So it has more than 80,000 individuals with various different mental disorders and controls. These individuals are selected from the baseline cohort, which has all the individuals born in Denmark between 1981 and 2005. And this control is the population control, meaning the controls are randomly selected from the entire population. So it's a population-based control. And after identifying these individuals, they have been linked to their DNA, their blood spots stored in the neonatal screening biobank, and using that blood spot, DNA is isolated and then is genotyped. And these individuals' information regarding civil, employment, hospital, psychiatry, education, all this can be retrieved from the Danish registers, and everything can be pulled together in a highly secure server where it is available for all the researchers to do very interesting research. And one of those research is this interesting project I'm presenting to you. So, study 1. So this is the title and the authors list. So it's about educational attainment. So what is education attainment? So it is just simply put, it's the highest level of education attained by an individual. Whether the individual completes school or college or university, There is a standard way to define the education attainment of an individual. It is put forward by International Standard Classification of Education, as you can see here. So why is it important to study education attainment? So education attainment informs about the cognitive health of an individual during early years of life, which is very crucial part in our life, where we know it's a critical period of brain development. And it is also a strong predictor of various outcomes later in life, like health, socioeconomic, behavioral outcomes. So what we know about the genetics of education attainment is substantially heritable. We know that from twin studies, family-based studies, that monozygotic twins have more correlation of education attainment than dizygotic twins. So what about genome-wide association study of this phenotype? So here we have so far 3 large GWASs have been published, extremely large GWASs have been published for education attainment. The first one was published in 2013 in more than 100,000 individuals. The second one in 2016 in more than 300,000 individuals, and the third one was published just recently last year in more than 1 million individuals. So we have learned a lot of things from these studies, and so what any extra information am I going to learn using considerably a small sample size like 35,000 from the eyesight cohort? But we realize it's actually a unique data set of what we are having. So what is special about this data set is that first thing is this information is available not just for normal individuals, but we also have this information for individuals with different psychiatric disorders. So one could answer the question, what is the genetic architecture of education attainment is different between an individual without a psychiatric disorder and with a psychiatric disorder. And the second thing is, so far the education attainment GWASs have been done using a very coarse phenotype, that is number of years you stayed in school. But here, the information we have is a fine phenotype, which is the grade, school grade, in the 9th level exam. So individuals with exactly the same number of years of schooling can vary differently with their school grades in math and Danish grades. So we capture more fine information. So we conducted a GWAS and with the following aims. So first to conduct a GWAS for school grades and then study the genetic architecture of school grade, then compare the findings with the previous GWAS findings, and then construct polygenic risk score for school years in ISIC individuals and predict the school grades, and finally conduct separate GWASs for Danish grades and math grades to see is there any difference in the genetic architecture between the two. So materials and methods. So we have after QC like 32,125 individuals, then phenotype. So we have like math and Danish school grades, and given at the 9th level exam at the end of compulsory schooling in Denmark. And the genotype after QC we have around 5 million variants with minor allele frequency greater than 1% for the final analysis. So results, first genome-wide phenotype distribution. So we, as I said, that the individuals are not just normal individuals but also individuals with other psychiatric disorders. So first is the effect of sex, that is females score a little higher than males, which is also what we know from previous epidemiological studies. Then this is all, here you can see the effect of psychiatric disorders on the school grades. ADHD individuals scored the lowest and individuals with anorexia nervosa scored the highest. This pattern also what we know from the previous epidemiological studies, and it is beautiful that we capture the same in our data. So of course we know that the psychiatric disorders has an effect, so we did this GWAS analysis. In addition to all the routine covariates, we also included psychiatric diagnosis as an additional covariate. So what we found? We found 4 genome-wide significant loci with p-value less than 5×10⁻⁸. And what is special about this interesting is that when we actually looked up the association of these loci from the previous study of school years, we found that almost of 3 variants are strongly associated with school years, which says high replication. And in addition to that, we also conducted a genetic correlation between our phenotype, which is school years, and the previous phenotype, that is school years, school grades with school years. Then we found that there is a very high, extremely strong genetic correlation. We simply suggest that there is a high genetic correlation between how an individual will perform in Danish and math exams, so the 9th level exam, and and how many years of schooling the individual will have in his whole lifetime. Then polygenic score analysis. So we used the SSGAC, that is the previous GWAS, as a training sample. We retrieved the betas from those summary statistics and used to construct polygenic score in our sample. This is the target sample. And we actually assess the performance of this polygenic score using a value called adjusted R-squared, which simply explains how much of variance in the phenotype is explained by your polygenic score. So we did this in all samples together, and we also did this in individual psychiatric disorders separately and also in controls. So this is the results where the R-squared values are shown as bar plots. In the x-axis you have the different groups, and the y-axis you have the adjusted R-squared. So the first group is the analysis from all samples. We did this analysis using 10 p-value threshold, 10 polygenic score, each corresponding to a specific p-value threshold, starting from genomewide significant threshold all the way down to 1, which means essentially we include all the SNPs in the construction of the polygenic score. You can see that there is a strong association between polygenic score and the school grades, and the R-squared value, the variance explained, is up to a maximum of 7.8% variance. And what was interesting is when we actually repeated this analysis only in the each psychiatric disorder separately and in the control, we found that in the controls the variance explained is way higher, up to 11.4% in compared to psychiatric disorders. In contrast, in ASD and ADHD, it has almost half of what the variance explained in controls, which simply reflects the negative association that we know that exists between the psychiatric disorders and education attainment. Then we actually divided the entire samples into 10 deciles, and then we, based on the polygenic score, and then we visualized the distribution of the school grades for each of these deciles. And what we found is that, so each of this bell curve represents the distribution of the school grades in each decile. As the decile increases, we can see there is a shift in the mean school grade from decile 1 to decile 10 in a linear fashion, step by step. That is like a beautiful linear relationship. It is known for only very few phenotypes in the genetic literature, like height. And then we did an interesting comparison. So we actually repeated this analysis, but we used only the control individuals. So, and then we divided them into 10, and then we took the control individuals, that is individuals without any psychiatric disorder in the decile 1 who have extremely low polygenic score, and we compared their school grades with individuals with ADHD. So why we chose individuals with ADHD as a comparison group? Because among all the psychiatric disorders, individuals with ADHD had the highest, strongest negative association with education attainment. So we chose ADHD, and what we found is that control individuals who have extremely low polygenic score performed worse than even individuals with ADHD, which suggests that the effect of extremely low polygenic score for education can be more detrimental to school performance than the effect of ADHD on school performance. So next we wanted to see if there is difference in the genetic architecture between Danish and math grades. So the straightforward approach is to just do a GWAS for math grade and Danish grade, and that's what we did. So before seeing the results, so here is a scatter plot of the phenotypic correlation between Danish grades and math grades. We observed a highly strong correlation, 0.61% correlation between Danish grades and math grades. And when we did the GWAS, and then we did the genetic correlation, we see a very high genetic correlation between these two phenotypes. And these two phenotypes were also strongly correlated with the school years GWAS as well as school grades GWAS. So what we learned from this research is that whatever the genetic factors we are capturing from these GWASs, they all probably are capturing the same signals, same genetic signals that enables an individual to perform well in Danish, to perform well in math, and also to attain many number of years of schooling. Probably what we assume that genetic factor is genetic factors for general cognitive ability. But we were not interested in that. So what we were interested is that these guys, so who perform well in math but not in Danish, and who perform well in Danish but not in math. So what and gives them, the specific ability to perform selectively in this special thing in one of the subjects. So to do that, what we did is that we repeated the GWAS, but this time we adjusted the Danish grades for their math grades and their math grades for their Danish grades. So we included math as a covariate. And what we found, we repeated the genetic correlation analysis, and we found there is a strong negative correlation between these two. And surprisingly, these two phenotypes were equally positively correlated with both school grades and GWAS, school years GWAS. So it says that these two phenotypes, they are like a heterogenic phenotype. They have a lot of multiple subphenotypes within them, and the Danish-specific signals is within them and math-specific signals within them. So we need to break them down to study more about their associations. So some of the results from these two GWASs. So genome-wide significant loci. So we identified one locus for math-specific GWAS and none for Danish-specific. And what is special about this math-specific locus is it's strongly associated with intelligence, but it is not associated with education attainment. This suggests that this locus is specific for intelligence. And then we did a genetic correlation analysis. We analyzed over 60 phenotypes, and for 13 phenotypes, we found that the genetic correlation of Danish-specific GWAS was significantly different from the genetic correlation of math-specific GWAS with these 13 phenotypes. And what's shown here in the x-axis, you have the genetic correlation. On the right side, positive, on the left side, negative correlation. The blue corresponds to math-specific, and the red corresponds to the Danish-specific. So what the result says here, so it says that if you have a high genetic predisposition for math to perform well in math, probably you are protected against being alcoholic or a smoker or to smoke cannabis, and also you're protected against neuroticism, schizophrenia, and major depression. But sadly, you will have very few number of sexual partners, and probably you will be pretty old by the time when you have your first sexual intercourse. So, what about Danish-specific? So, if you have extreme ability for reading and writing, genetic predisposition to perform well in Danish, then probably you will be a smoker, but thankfully you won't be a heavy smoker. So, and you will be a curious person, so at least once you would have tried cannabis in your lifetime. And then here comes the most interesting part. The extreme ability to read and write also comes at a cost. So you will be at risk for developing schizophrenia and major depression. We were interested by this finding specifically because this also in line with the previous result study from Icelandic population, where they show individuals with very high genetic, polygenic risk for schizophrenia and bipolar disorder are often involved in creative professions like music, art, painting, and so this also in line with our finding, where we see the Danish-specific ability, which can be considered as the reading and writing skills, having a positive link with schizophrenia. To summarize, we found that the genetic architecture of school grades is highly similar to the genetic architecture of school years. Polygenic scores for school years is highly predictive of school grades, and we found there is a significant difference in the genetic architecture between Danish-specific achievements and math-specific achievements. Limitations, so first one is that we are studying here only individuals who went to school. So a lot of individuals with psychiatric disorders doesn't go to school. So our interpretation could be biased, particularly, for example, I say that I compare the control individuals with ADHD and say the effect of polygenic disorder is more on controls than the effect of ADHD, but the effect of ADHD can be so severe that the individuals don't go to school at all. So you have to remember that my interpretation here is individuals who can go to school, and that it's only restricted to those group of individuals. So the second limitation is, of course, anyone will come with this question when you come across this kind of studies that what about socioeconomic status? So of course we agree that a large proportion of this effects, whatever I show you, is mediated by the socioeconomic status. But it is very complicated, because the environmental factor, particularly the socioeconomic status, is highly intertwined with the genetic factor. So the socioeconomic status reflects the education of the parents, and the education of the parents is because of their genes, and those genes are what we are studying here in the children. So it is not a straightforward way to account for the socioeconomic status in these kind of studies. And finally, we have study sample who are highly enriched for psychiatric disorders. So some of the findings, like from dance-specific, math-specific findings, we are not exactly sure if this applies to the general population. But with the new phase of ISAC data, we hope to have a large sample size for controls where we can repeat the same in the control individuals and see if we are seeing the same results. Study 2. So we did a genome-wide association study for developmental disorders of speech, language, and scholastic skills. A little bit of background. So speech is the ability to convey information to others, and language is the ability to understand others speak. And scholastic skills is just the ability to read, write, solve basic math problems. All these skills are cognitive skills. So when you say a child is suffering from a speech disorder or language disorder, you compare the speech ability of the child with the children of the same age group and see that the child is not having the skills expected to have for his or her age group. Then you say this child has a speech disorder or language disorder or scholastic skill disorder. So these disorders, so they are very common. 5 to 10% of the school-going children used to have these disorders, at least in the milder version. And sometimes they go undiagnosed and they suffer from some social interpersonal relationship or emotional behavioral problems when they grow into adults. So what is the cause for this disorder? Most often it is genetic. And what we know about the genetics of these disorders so far. So I'm going to show you this plot again. So where that we have common variants and ultra-rare variants. So like I told you before, like in the previous study, we were dealing here, but in this phenotype, most of the studies that's been done so far are they somewhere lie in the middle of this spectrum. That is because those studies were based on families who have children with speech problems, and most often these children will have severe disease for the parents to seek medical attention. And such studies have identified dozens of genes where, like FOXP1, FOXP2, where if you have a mutation, almost sure the child will have a speech problem or a language problem. But there are a lot of children who don't have such kind of mutations, but like they have mild to moderate disabilities in speech and language. We do not know why. We think that it might be because of common variants like what we see for other diseases. But so far, the studies that have been done using common variants are very few studies we have, and those are like based on small sample size, and the results were they haven't found anything. So still we have a lot to find about the common variants in these disorders, and that's why we did this study. So the aims of the study is to study the common genetic variants associated with these disorders, and then to construct polygenic score for IQ and education attainment and see how it is compared to controls in these disorders. So methods, the sample are same, again from the same ISAC cohort, and then we identified the cases using electronic health records based on the ICD-10 diagnosis, F8D for speech and language disorder and F81 for scholastic skill disorders. Then we have our 5 million variants to study. And one important thing is you can see the sample size here split based on the psychiatric diagnosis. So ISAC is established basically to study major mental disorders. So this is a secondary phenotype. So most of the individuals we identified based on electronic health record has comorbid psychiatric disorder. So what we did is we also took the individuals with psychiatric disorders and we put them in the controls, and then we adjusted for psychiatric disorders in the diagnosis. So results and discussion. So we did 3 GWASs, one for speech and language, one for scholastic skills, and one for both disorders together. And in the speech and language, we found two loci. One is at the chromosome 6, and the other one is the chromosome 17. And in both of these loci, we have genes like, for example, here XCSBP5, which codes for a protein called tomosin, which is involved in synaptic neurotransmission in the brain. And in this loci, you can see, in this locus, you can see there is a gene UBTF, which is a transcription factor, and the risk variant is located right on the exon of this UBTF. And previous studies have shown that pathological mutations in this gene will lead to speech problems. So both these loci, so already when implemented, it's shown to relate to neurodevelopmental disorders. So then we did polygenic score analysis. Then we constructed polygenic scores for these group of individuals and controls using two phenotypes. One is IQ, other one is education attainment. And we compare, just our question is very simple. If individuals with speech disorders have a low polygenic score compared to the controls or the general population, and that's what we found. So these individuals, you can see this negative beta values, which means that these individuals have lower polygenic score. So from the clinical setting, we know that these individuals have cognitive deficits. So this kind of says that the cognitive deficits in these individuals could be partly explained by common variants associated with cognition in these individuals. So to summarize, we found two genome-wide loci for speech and language disorder, and both loci implicate neurodevelopmental disorders. And then we found there is a polygenic score for IQ and education attainment is low in these individuals compared to controls. So limitations, of course, it's even though overall it's a big sample size like 70,000, the cases is very low. It's like 1,300 and 1,500, so it's a small sample size. And there is heterogeneity in the case definition. I told you F80 and F81, but the actual thing is under F80 there are multiple subtypes, under F81 there are multiple subtypes. And we kind of just assume that they all fall together in a single category, but we do not know how heterogeneous the genetic architectures are. So to study that we need a larger sample size. And the samples are not representative of the population. This is the most important limitation. Our research just doesn't say anything in general about speech and language disorder. So we are not sure if the results are general for speech and language disorders, or it applies only to individuals who have speech and language disorder and also have psychiatric disorder. Then ascertainment bias, all these are based on electronic health records, ICD-10 diagnosis. We do not know exactly how much of the time the psychiatrist accurately profile the patient and then give the diagnosis. A lot of times these ICD-10 diagnoses are given for insurance reasons. So then the third study is titled is Brain-Specific Transcriptome Imputation Identifies Multiple Genes Associated with ADHD. So what is ADHD? It stands for Attention Deficit Hyperactivity Disorder, and it's a childhood psychiatric disorder characterized by hyperactivity, inattention, impulsivity. Around 8.5% of the children and 2.5% of the adults have ADHD. So individuals with ADHD struggle in school, that's what you saw in our first study, and then they have mild to moderate levels of cognitive dysfunction. What we know about the genetics of ADHD, coming back to this plot again, so we have these common variants and rare variants. Both common and rare variants contribute to ADHD, but the contribution of common variants is however substantial. How we know that? Very recently, ISEC has published the largest GWAS of ADHD, and one of the important, so this is the first successful GWAS for ADHD, and what we found is that around 22% of variation in the phenotype in ADHD could be just explained by the common variants in the population. And many genes that we found that they found in the ADHD GWAS are also found to be brain specific. So we asked, okay, so what genes are differentially expressed in the brains of individuals with ADHD? So we wanted to do this study. So in an ideal scenario, if you want to do this, all you have to do is collect both brain tissues from ADHD individuals and brain tissue from controls, and then compare the gene expression, quantify and compare the gene expression. But there are problems with that, you cannot just get brain individuals from living individuals, so I don't think they'll be comfortable with that. So, but you can also get the brains from postmortem individuals, but in order to do a study with high statistical power, you need thousands of postmortem brain. Let's say even if you collect it, it's gonna take a lot of 10 years or more, and then a lot of staff and cost to do the quantification of this gene expression measurement. So what's the alternative option? So there is an alternative option. So instead of so taking the brain and measuring the gene expression, you can just take the blood and do a genotyping, and based on the DNA variations, you can predict what would be the gene expression in the brain of these individuals. So we can do this today because we have a lot of computational methods available, and one of the computational methods is called PredictScan, and that is what we used in this study. So what is PredictScan? So PredictScan predicts the expression in any tissue in the body based just on your DNA variation. How it does that? So it actually uses something called as reference transcriptome dataset. It is the dataset where you have measured both gene expressions as well as the genotypes in the same individual. So there are like a lot of such data sets available today. Like for example, GTEx, who collects tissues in massive numbers from postmortem tissue, and then they study how the genetic variations affect the transcriptome, the gene expression. So Prediscan uses such publicly available data sets, and then it constructs prediction models, and then using these prediction models, it predicts the gene expression. Due to time constraint, I'm not going to go deep into this prediction model construction, but all you have to know is that using this model, we can just predict the expression in a target data set where you have only genotype information available. And in this study, the target data set is eyesight. So let's say that I have to compare the gene expressions in the prefrontal cortex of individuals with ADHD, without ADHD. Then I have to just predict the expression, compare, and at the end of the analysis, I get z-score and p-value. Z-score says if the direction of the association, that is if it is positive, then it is more highly expressed in cases than controls, it is negative, highly expressed in controls than cases. And what's the problem here is if you want to do this in hundreds and thousands of individuals, easily it will become computationally intensive. There is an easy way to do this. So instead of doing this way, we can actually just run a GWAS analysis using the same sample, get the summary statistics, and then use a reference genotype. Then you derive the same z-score and p-value of what you get from this direct comparison. And this can be done using Metascan, which is just a modification of Prediscan. And what we used is like Prediscan, Metascan here. And methods. So here we actually use the summary statistics from the most recent ADHD GWAS, which comprised of 20,000 ADHD cases and 35,000 controls. And we tested the gene expression. We predicted the gene expression in 13 brain regions and all brain regions, and mostly from GTEx and one from the complementary consortium. So results. So what we found is that we identified 105 significant associations, and these 105 significant associations correspond to like 53 genes, differentially expressed between ADHD and controls. And these 53 genes are shown here in the y-axis of this heat map plot, and the 13 tissues in the x-axis. So you can see that the same gene has been implicated in multiple tissues, and importantly, the direction of the association is consistent across the tissues. At least one significant association was identified from each of the brain tissues. So now we have this 105 associations. So our question is, there was already a big ADHD GWAS, and they have found a lot of things. So what new thing are we going to find from this analysis that we don't know from the previous analysis? So this is the Manhattan plot from the ADHD GWAS. On the x-axis, you have the chromosomes, and the y-axis, the p-value in log 10 scale. Each point corresponds to each variant in your genome, and the towers correspond to the significant loci. They found that 12 genomewide significant loci for ADHD. So the question is, how these 12 genomewide significant loci increases one's risk for ADHD? We do not know that, but what we can do is just zoom into these regions and then see, okay, what genes are located there. Then using some additional database, you can say that, okay, gene A is associated with ADHD probably through some mechanism. And like a lot of mechanisms are possible, and one of the mechanisms is gene expression regulation, precisely what we are studying in this project. So let's take the chromosome 1 locus, and then we zoom into this locus, and here you can see in this locus, there are like a lot of genes are located. So we don't know like which gene precisely causes ADHD. So which variant to link to which gene that will lead to ADHD. So here where our study comes into play would help a little bit in the interpretation. So this is a different version of the Manhattan plot, what you saw before. The points are just dull in the background, and then the red color pinhead correspond to the 12 loci. And then the genes that we identified, 53 genes, are shown here as blue lines, that a lot of genes clustered in the same place. So you can see, for example, let's take just one gene in the chromosome 1 locus, MED8, which codes for a protein called mediated complex subunit 8. It is a transcription activator, so clearly it is involved in the transcription of the gene. So let us zoom into this chromosome 1. So how we found this MED8 is that we predicted this MED8, and then you can see that individuals with ADHD have lower expressions statistically significant, lower expressions compared to controls in the prefrontal cortex. So let's zoom into this chromosome 1 locus, and then you can see that here is MED8 located. So very close to the genomewide risk locus, and we use like 72 SNPs to predict this expression. And among the 72 SNPs, which are actually shown as red color dots here, you can see many dots are beyond genomewide significant, and they are genomewide significant risk variants. So we can say that the risk variance here could contribute to ADHD through altering the expression of MED8 in the prefrontal cortex. So here we use 71 SNPs and almost 19 SNPs are in LD with genomewide locus. Like this, we found like many genes which can interpret that in a similar way. So then we wanted to replicate. We have no ADHD sample available for replication. So we used a proxy phenotype where they measured the ADHD symptoms, that is inattention and hyperactivity in children, in a lot of children and adults. So like 17,000 people, and these are not individuals with ADHD, they are very normal individuals, but their tendency for ADHD symptoms are measured. What is interesting is that these two phenotypes highly correlate, it's almost one, that's finding from the ADHD GWAS. So we have justification to use this as a replication phenotype. So we asked, okay, so of the 105 associations, how many are also associated with ADHD symptoms? Surprisingly, it's just 22. Remaining 83 are not associated. This is something that you just see by chance. So there is no replication here. So we thought about it, so why there is no replication? So you can see here that first there's like genetic risk variants that cause ADHD, genetic risk variants that cause ADHD symptoms. And what we know already is that at this level, there is a 100% correlation. In the study, what we assumed is that this mediator would be the gene expression, and we studied the gene expression. And we predicted the gene expression in both the types, but what we found is 0% correlation. So what's happening here? When you see a 100% correlation here, you don't see any correlation at this point. So right now, we don't have the exact answers, but there are like multiple possibilities. The mediator is itself something else, so probably these risk variants cause ADHD through some other mechanisms than gene expression regulation. Or maybe we are not looking at the correct brain tissue. We have to look at the correct brain tissue to get this correlation. Or it is also possible the individuals in the prediction, the reference transcriptome data that we use, most of them are older individuals, like about 40, 60 years, but here we are studying a phenotype that occurs in the children. So probably if we use brain samples from children and then use construct prediction models, it might reflect more the transcriptomic architecture in the brain during younger age. But we do not know that, only future studies will tell it. So we conducted, to summarize, we conducted the largest GWAS of ADHD. We found 105 associations, and many were driven by genomewide loci. And then our findings, we tried to replicate, it did not replicate in a related phenotype. Limitations, there is no appropriate replication sample, and then the prediction models are not available for all genes. So when I say these tissues, like mostly we are working on 30 to 40% of the genes. There is 60% of the genes we don't have any prediction models because we don't have a large sample set to capture the heritability of these genes. So it is very much possible that those genes also cause ADHD, but we are just not looking at it. So age-appropriate RNA-seq datasets, that's one of our guesses, could help to replicate the findings. So closing remarks. So technology has advanced faster than anyone has ever imagined, and genome-wide association study is an excellent example of how technological advancement has enabled scientists to probe human diseases. In the first half of the PhD dissertation, we used GWAS as a tool to study the genetics of cognitive function in the general population, also the genetics of disorders related to cognitive function. And what past studies have informed us is that it is not always necessary. You have to do exhaustive cognitive assessments in a laboratory setting to probe to understand the cognitive mechanisms. A very simple phenotype, like number of years one individual attended in school, could give you a lot of information provided if you have sufficient sample size. And we followed the same footsteps of these researchers, and we conducted a genome-wide association study by using Danish grades as a proxy phenotype for cognition. and we found a lot of new exciting information that was previously unknown. Then, on the second half of the dissertation, we have now thousands of GWASs has been published, successful GWASs in millions of individuals, but still we have a lot of problems to tackle. One of the problems is to answer the question, how these risk variants lead to the disease. Many mechanisms are possible, and in the second half of the PhD dissertation, we addressed one of the mechanisms, gene expression regulation, and we used ADHD as an example phenotype. So our study informed us that it's not as simple as we imagined that we can identify genes for ADHD, but still we learned a lot from our experience, and we will use our knowledge in improving these methods in the future, and in the process we will use this to study also cognition. So some people will say that what we are doing is reopening the Pandora box of eugenics, but our intentions is crystal clear. We are not really interested to create any super smart humans, and we don't think it's even possible in the next 100 years. But what we are interested to help individuals who suffer to have even a normal cognitive health. Imagine parents who have their children who have cognitive deficits, who difficult to catch up with their peers. It's difficult to live with a health problem, but it's very difficult. More than that, it's very difficult to live without knowing why the health problem occurred in the first place. We are trying to help them to understand what their child is going through, and we need your support. Thank you.